In our past few videos, we've had a chance to talk about the derivative and higher order derivatives. We've seen that we can find the second derivative of a function. Sometimes we can even find the third, fourth, or fifth derivative, although that doesn't always have a specifically relevant or practical application in terms of its meaning, but it is still possible. We also touched briefly on the fact that we can work backwards and find an antiderivative through the process of integration, which you'll learn more about if you take math in university. And another topic that we've touched on briefly, but not gotten into in too much depth, is curve sketching. And that's what we're going to look at today in this video. Let's start and see what's going on in our slide here. So curve sketching and the second derivative. Just by looking at the following graphs, we can have a pretty good idea about their concavity. So let's start by looking at our graph on the left. Pretty basic parabola. In fact, this is our parent function, f of x equals x squared. So no transformations. This is as simple as it gets. And what do we notice about our tangent lines? Well, let's take a few random points. Let's sketch some tangent lines to those points. And look for a trend in terms of where the tangent lines are located. We notice that all tangent lines are below the curve. And this tells us that this is going to be concave upward. So concave, in terms of the concavity, we can think about it. We have the smile. Smiles are happy and positive, and so this is going to be a concave upwards. So my second derivative has a positive value. Alternatively, in my other example here, where my parabola is opening downward, so it's the exact same shape. It's just been reflected about the x-axis. Let's sketch our tangent lines. And what do we notice about these lines? Well, they all appear to be above the curve. So in this case, all tangent lines are above the curve. And if we think about the shape the graph is making, it's going down. It's a frowny face. It's feeling negative. So it's going to be concave downwards. Let's verify this algebraically by actually calculating the second derivative. So working on the left, first of all, with our parent function. So we have f of x equals x squared. Let's find the first derivative. We're just going to use our power rule here, bring the 2 down, 2x to the power of 1. I don't need to write the 1. Let's find our second derivative. F double prime of x is equal to 2, or 2 times 1, which is just 2. And we'll note that this is always positive because the value doesn't change. So if it's positive 2 to begin with, or at a given point, it's going to be always positive 2. So we'll note that f double prime of x is greater than 0 for all x values. And therefore, f of x is, and we describe this as concave up or concave upwards for all x values. So throughout its entire domain. We didn't really talk about domain and range directly in this course though, so I'll try not to use those words if you haven't taken advanced functions and aren't familiar with them. In our second situation here, my f of x is equal to negative x squared. Let's find our derivative. And then our second derivative. So f prime x negative 2x. F double prime of x is equal to negative 2. What do we notice? It's negative everywhere, or always negative. So f double prime of x is less than 0 or negative for all x. Therefore, we can say that f of x is concave downwards for all x values, or for all throughout its domain. All right, so we saw visually by thinking about the smiley face and the frowny face. And we could also confirm mathematically by determining if the value of the second derivative is positive everywhere. Any region where it's positive is going to be concave up, and regions where the second derivative is negative are going to be regions where we are concave down. Unlike quadratics, unlike parabolas, we notice that higher order polynomials can have multiple intervals of different concavity. So if it was just, parabola, I'd just have a shape like this, concave down everywhere, that's fine. Or maybe a shape like this, concave up everywhere, that's fine. But in this case, we have a mix. We have regions where it's alternating, and this is already color-coded, but I'll do it again just to talk you through it and demonstrate. Everywhere here, my slope is increasing. So my y value is increasing, but my slope is decreasing till it reaches 0, and then it starts going down and have a negative value. So we have that overall impression of forming that arch or that curve. So concave down here, same thing here. And in between we have the regions where it's curving upward. So we have regions of concave up, and we have regions of concave down. So we need to be able to identify where those regions are happening and describe accurately which is which. Describe which regions are concave up and which regions are concave down. Let's add a couple labels here. So what is happening at these points? The concavity is changing. Concavity. I need to double check my spelling as I go sometimes too. Concavity changes. And these are our inflection points. Where else are we going to have inflection points? Also here. And here. And this is a 5th degree polynomial that's mentioned up here in the question. I kind of forgot to mention that. 5th degree polynomial. And so let's think about what pattern, what do we know about 5th degree polynomials? Well, I know it's going to have n minus 1 turning points, where n is the degree of my function. So how many turning points do I have here? How many times does it change direction? Well, 1. Actually, I'll use a different color for these. 1, 2, 3, 4. So 5 minus 1 equals 4 turning points. And I can have n minus 2 inflection points. 5 minus 2 is 3, and we identified, inflection points, and we identified, so turning points, max or mins, and inflection points. Inflection points where the concavity changes. So 5th degree polynomial, we predicted 4 turning points. We saw 4 turning points. We predicted 3 inflection points. We found 3 inflection points. So everything looks good. And this is a general rule. So let's write that somewhere. My turning points, my number of turning points, the maximum number is going to be n minus 1. Inflection points is going to be n minus 2, where n equals degree of the function. As in my f of x, we're not talking about derivatives or anything quite yet. We've taken a look at this visually and talked about the mathematical relationship between the degree and the points a little bit. Let's move on and fill in some blanks here. We will note that if the second derivative, so if f double prime of a, so remember a just means we're looking at some specific point on the graph. If f double prime of a is greater than 0, then f of a is in an interval that is concave up. Moreover, if f prime of a equals 0 as well, then we can go further and say that the point a comma f of a is a local minimum. Why is this so? So we're going to point out that if f prime of a, and so that's our first derivative, so be careful with our notation here. In fact, I'm going to write this a little more clearly just to avoid any confusion. If the first derivative of our function at this point is equal to 0, then there might be a max or min. But in this case, we have 2 pieces of information. So if f prime of a equals 0. So I know this is 0 point in the slope, so I know it's a max or min in my original graph. And the second derivative is greater than 0, which means it's concave up. Then we know it's a minimum. Then the y value at that point, then f of a is a minimum. So we need two pieces of evidence to determine if something is a max or min. I need the first derivative to be 0 at that point, and I need to determine the concavity, if it's opening up or down, by using the second derivative. Moreover, next part, if f double prime of a is less than 0, then f of a is in an interval that is concave down. So second derivative has a negative value. Negative is unhappy, so we got our sad or our frowny face. Moreover, if f prime of a is equal to 0 as well, then we can go further and say that af of a is a local maximum point. Why is this so? Well, once again, if f prime of a equals 0, then I know I'm at a point where my tangent has a slope of 0. And f double prime of a is less than 0, then that tells me that it's concave down. So it tells me I have that pattern of increasing slope, 0 slope, and then decreasing slope. That's what concave down is describing. Then we know that the point, that y value, f of a, is a maximum. So I'm defining this point right here where my x value is a, my y value is f of a. If f double prime of x equals 0, then f of x has a possible point of inflection, or inflection point. We just use those interchangeably. We're saying the same thing. And remember, what does an inflection point look like? At some point on our graph where it's changing from concave down to concave up. I don't like how I drew that. So maybe concave down to concave up, or concave up to concave down to concave up, where the concavity changes. Couple notes though, let's read through this carefully. Don't assume that you have a point of inflection. You must check to see that the sign of the second derivative changes on either side of this point of interest to be sure. So basically we need to take a test point here and make sure that the value is different, that one is positive and one is negative. So this is concave up here, this is concave down here. So I need to make sure that my second derivative value is changing from positive to 0 to negative. And similarly here we have concave down, here we have concave up. So I need to look for that pattern by taking some test points and seeing that in those points it's going to go, my second derivative has a value of negative, and then 0, and then plus. So we're going to be talking about that later in this note. We're going to use tables to organize our data and do some tests around our points of interest to prove that they are local max or mins, or points of inflection, or inflection points. Note also that it is possible to have a point of inflection or simply a change in concavity in some situations where f double prime of x doesn't exist. For example, concavity can change across a vertical asymptote, CA. So let's take a look at A for a moment. We can see here, as I'm approaching from negative infinity, that my graph is curving up, so we can kind of complete our smile there if we wanted to. After my vertical asymptote here, I can see that my graph is curving down, and we can kind of complete the frowny face here if we want. You don't need to draw the faces, it's just a tool to help you remember. So we see there's definitely a change in concavity here. So we can also consider that the value of my second derivative is going to be positive in this region as I come from the left, because it's concave up. In the second region here, it's concave down, so it's going to have a negative value. And in the middle, it does not exist. It's not defined there. There are no y values. It's an asymptote. It's a value that does not exist. And the limit doesn't exist either because it's approaching two separate values from either side. So that's A, or there can be a point of inflection at a place where the second derivative does not exist. See example B. Once again, if we were to cut this in half for a moment, that's where our concavity is going to change as I approach from the left. We can imagine our smile, positive, concave up, so the value of my second derivative is positive at this point. Afterward, you can imagine it's curving down, so our frowny face, so concave down. And what's happening in the middle here? What's the value of my second derivative right here? It doesn't have meaning. It does not exist once again, because if I take my first derivative at this point, I'm finding the slope of this line, but right here at this point, my tangent is a vertical line. I can't find the slope of a vertical line. So if I can't find the first derivative, how could I find the second derivative? It does not exist at that point, and so that's where it's a little bit tricky. So watch out for that. I should be careful of that even in my own example as well here, because here I wasn't really careful. If I kind of drew this as a vertical line, so let's actually fix that up just to be clear. So maybe we have something like this instead, where it switches. Actually, I'll be a little more precise here once again. So it's definitely not vertical at any point, because as we've discussed before, we can't find the slope of a vertical line. That's something that you talked about in grade 9 already. Something like that. So at those inflection points, my second derivative has a value of 0. All right, I think that's all we have to say about that in this graph. So just know, look for the second derivative to help guide you in terms of identifying local maximums, local minimums, and points of inflection. But know that we also need to examine points on either side of that point to be really sure it's actually an inflection point, that it's actually a local max or min, and also to watch out for the fact that concavity can change if there's a vertical asymptote, or if there's the tangent has a perfectly horizontal, or if the tangent would be perfectly vertical at that point. So in this case, just to be clear, we do have an inflection point, but we cannot find the second derivative there. It's not defined. All right, curve sketching and the second derivative. This question is asking us to examine the graph and answer questions about where it is concave up and where it is concave down. Let's start with our first question. On what intervals, so in which part of the graph for what x values is f of x, so remember that's like my y value, or we can think of it as just my function, concave upwards. So for what values will my second derivative be positive? We don't have to do any calculations here. We just want to look at our graph and think, where's the smile occurring? So we could help extend this just to help visualize, and we see that it's occurring here. But of course, my graph doesn't actually extend upward here. It flips and goes down. So I'm going to have an inflection point here in the middle. And that inflection point is where the concavity changes. So as I move left to right, starting at this inflection point and moving right, those are the values for which my graph will be curving upwards, concave up. So how do we describe that? How do I denote that range? We can write it something like this. X is an element of 0 and positive infinity. Or we can do 0, comma, infinity. And notice that we're using the round brackets, so they're the non-inclusive. So it does not include the 0 value. It's everything after the 0 value. Or we can use set notation that I'm kind of more familiar with for working with this kind of thing. X is an element of the real such that x is greater than 0. And it doesn't really matter what notation you use. A specific problem set or textbook or a professor might ask you to do it a certain way. I don't really care as long as you're consistent. Next, on what intervals of f of x, on what intervals is f of x concave downward? We can kind of obviously predict. There's only one inflection point here. I'll leave that labeled. So we already identified the concave up portion. The rest of it has to be concave down, but we should be careful because we know our higher order polynomials can change direction a number of times. So we look carefully at our graph, and I see that my frown is kind of occurring here, and that the actual graph only goes up to the inflection point and everything that came before it. So what is our interval of downward concavity going to be? Once again, I'll write it in a few different ways. We can either say x is an element of negative infinity to 0, or we can just write negative infinity to 0. So basically, I can go as far to the left as I want, and it's always going to be concave down. Or, once again, the notation that I'm more familiar with, set notation, x is an element of the real, such that x is less than 0. And once again, it's not less than or equal to. At the 0 point, it is neither concave up nor concave down. It is a point of inflection. It's a place where the concavity changes, so it does not have its own concavity at that point. A point where an unbroken curve changes from concave downward to concave up, or vice versa, is called a point of inflection. We've seen that before. Where is there a point of inflection in f of x equals x cubed? We've already seen this. We've already identified it. We don't have to do any mathematical calculations here, although I could pause and find the derivative and the second derivative if I wanted to and verify. But instead, I'm just going to read it right off the graph, and I'm going to indicate that that point is at the origin at 0, 0. Zoom out so we can take a look at the whole page for a moment, and then we'll move on to our next page. Now that we are experts in looking at graphs and identifying concavity, there we go. I'd like you to take a few minutes to investigate intervals of concavity. So if you're watching this live in class, you can pause the video now, and actually I'll probably stop the video here and record the next part as a separate video. But I'd like you to pause and actually try this investigation for a bit, get a feel for identifying regions of concave up and concave down, so regions of different concavity and the location of inflection points, using the link here to the CEMC OpenCourseWare. I'll also put a link in the video description for anyone who's watching and not in my class. The basic idea, though, is that you want to try to predict where the curve is concave up and concave down. And then there's a little slider on the bottom here, and as you drag that from left to right, it'll reveal the colors for the different regions of the graph, like we see here, and it'll show you which parts are concave up and which parts are concave down. So go ahead and pause or let this video finish, play with that for a few minutes, and when you feel comfortable with that, move on and watch the next video.